Hello guys, welcome back. We're going to do today some more notes on related rates and talking about how they apply to different geometric shapes and solving problems like that. Okay, so here's our first problem. We have the radius of a spherical balloon is decreasing at a rate of 2 pi. At what rate is the volume of the balloon changing when the radius is 5 centimeters? Okay, and I kind of walked through. These are the steps you're going to follow on any related rates type problem, no matter what shape it is. So we did circles in the last video. Now we're going to get something a little more complicated. But we're still going to answer the same question, right? So what's given by the problem? Well, they gave me this equation for a volume of a sphere, which, by the way, will always be given. You don't need to memorize that. The radius is decreasing at a rate of 2 pi. So the radius is decreasing, dr dt, and it's decreasing, so it's negative, equals negative 2 pi. At what rate is the volume of the balloon changing? So they're asking me to find a dv dt when the radius is equal to 5. Okay. So I've done the first two steps already, right? So I have my equation, I know the rate and the radius that's given to me, and I'm trying to go ahead and find the dv dt. Okay, so I need to write an equation first off, and this is always usually just going to be given to us, right? In this case, that's this volume equation that I wrote down that they already gave us. So start with that equation, volume is 4/3 pi r cubed, and then like always, we take the time derivative, that's using the implicit differentiation. And then after you do that, you plug in and then you solve. Okay, so when we take the derivative of this, so we're going to take a d by dt of both sides. So dv dt equals, okay, so we'll 4/3 pi, and then the derivative of r cubed. 4/3 pi is a constant, so that's 3r squared times the derivative of r. Now, a lot of the cool kids notice that the 3's cancel. So what you get is dv dt is equal to 4 pi r squared. So let's see, dv dt is what we're trying to find. So that's 4 times pi. The r is 5, so that's a 5 squared. And the dr dt, they told me, was negative 2 pi. So times negative 2 pi. So 5 squared, of course, is 25 times 4 is 100. So this is negative, let's see, negative 200 pi squared. And then the units here. Okay, well, let's talk about units, actually. So I want to talk about this. If you have, like, a distance or a length, that's going to be one-dimensional, right? A distance or a length would just be, for example, centimeters. If you had any kind of area or a surface area, that would be in terms of centimeters squared. It's two-dimensional. And then a three-dimensional quantity, like a volume would be centimeters cubed. So this is a good technique you can always use to help you know if you're dealing with a geometric shape, what are the units going to be? A length is one-dimensional, area is two-dimensional, volume is 3, and that's your exponent. So when we think about the units here, of course, we just do the units of v divided by the units of t. So that would be in terms of, let's see, volume is centimeters cubed, and the t in the problem, I see a second right there, so it'd be centimeters cubed per second. Okay. So that is number 1. Let's go ahead and take a look at number 2. So that was a sphere. Now we're going to have a different shape here. Okay, so now we have a cone of ice cream. So we have a cone, a pretty good cone. I love ice cream. I think we all do. Pillar of American society. It has a radius of 10 centimeters, or inches, sorry, and a depth of 20 inches. We're filling it with ice cream at a rate of 3 inches per second. So if we're filling it with ice cream, so it's filling up with something. Inches cubed also tells you it's a volume. That's telling me dv dt is 3. Okay, so let's go ahead first off. I have a visual here to show you what's going on. So if we take a look at this, this is a cone, and this is like just a different radius to height ratio, but take a look at what's happening, right? So we're filling it up with water, and then it'll start over, whatever. And then it's coming up, it's coming up, it's coming up, it's coming up. And we can see that at the start, the height grows pretty quickly, and the radius goes quickly, and then they start to slow down, which makes sense as it gets wider and it takes more water to fill it up. Okay, but one thing you'll notice is that this triangle between the R, the H, and the side of the cone is making a similar triangle. And that triangle is staying the same no matter how far we kind of go up there. So, okay, that's going to be helpful for us because when we do this, part A is asking me to write an equation for the volume in terms of the height of the ice cream. Now, this problem gave us the equation for the cone. So in part A, we start with volume equals 1/3 pi r squared h. And this told me to write an equation for the volume of the ice cream just in terms of h. So what I'm going to do is I want to write this in terms of h. And the way I'm going to do this is I'm going to use similar triangles to kind of draw a ratio between radius and height, just like you do in geometry. So if I were to draw some kind of situation here, like, okay, when it's full, I know the height is 20 and the radius is 10. But when it's partially full, so, the water, ice cream, whatever's up to here, it has some radius r and some height h. So if I set equal ratios, to each other, I say the ratio of radius to height is equal to 10 over 20. So this is the ratio when it's full, but it has that same ratio no matter what. And we know these triangles are similar, right? Because they have, the same angles along the way at the bottom. So that ratio of radius to height, when it's partly full, is the same as the radius to height when it's all full. Okay, so that tells me that r over h is just 1/2. So that tells me r is just 1/2 times h. I just multiply that to the other side. So in part A, when it asks me to write this just in terms of h, what I'm going to do is I need to plug in for r. So I need to plug in here for r, and that's where the similar triangles part is going to help me out. So this volume is going to be 1/3 pi times, okay, so that was h over 2 squared times h. So that's 1/3 pi times h squared over 4 times h. So that gives me a volume of pi over 12 times h cubed. So that's part A. Now part B asks me for the rate of change of the height when the height is 2. So part B says find dh dt when h equals 2. Now, once I have this equation, right, I have this equation right here that's just in terms of one variable. So I'm going to use the equation for part A and just take the derivative of that, right? And they told me, I know my dv dt, that's going to allow me to find dh dt because that's what the problem's asking me for. Okay, so let's go ahead and do that. So what I'm going to do is I'm going to differentiate this. So dv dt is equal to 3 comes down, so that's pi over 4 times h squared times dh dt. And then I'll plug in h equals 2. So my dv dt, oh my god, it cancels. That's so cute because 2 squared is 4. Is just equal to pi times dh dt. Okay, so that means that my dh dt is just equal to the dv dt divided by pi. So what is the dv dt? Well, the problem told me it was 3, positive 3, so that's 3 over pi. Now, in terms of my units, sorry about that, it's annoying. In terms of my units here, the units of volume would be in terms of inches cubed. And the only units of time we saw in the problem, I think I saw a second right there, so it'll be inches cubed per second. Okay, so that's how you find the dh dt. Now, part C says find the rate of change of the radius. So C is asking me to find dr dt. Now, one thing you could do is you could redo parts A and B and put everything in terms of r instead of h. But you can also solve these problems by just using this equation right here. You can use any equation that relates to the quantities. So I can use this. I can use r equals 1/2 h. So that means that my dr dt is always just going to be half of dh dt, and just take a derivative of that, which means it's just going to be half of the answer I got in this part right here. So half of 3 over pi, and that'll be inches per second. Also, I just realized that that should have been inches per second. I apologize for that. I'm really sorry. Okay. So what I was saying here is if you want to find this dr dt, you can use any equation. So if you have this relationship between r and h, you can use that because you know the dh dt right here. You could also redo this problem and just write everything in terms of r instead of h. It's just another way to kind of do the problem. Okay, so that's the count. We started by just writing the volume in terms of 1, then we found dh dt, and then dr dt. This is basically an old AP question, by the way. So I wanted to do one more problem here with a shape. So now we have a cylinder, and it's filling up with water at a rate of 3 cubic inches per minute. So again, it's filling up with some water, so that dv dt is equal to 3. This cylinder has a radius of 5 inches. So again, I'm going to try and draw a picture because I think that'll really help. The cylinder has a radius of 5. Find the rate at which the height is changing. So they're asking me to find a dh over dt. Okay, so what we have is we have this cylinder that's filling up with water like that. Now I'm going to try and give you a visual of what this would look like. So I have prepared something here. So go ahead and just stare at me, I guess. All right, so what I have is a cylinder. I'm going to hold this up here, and I'm going to fill it up with water. Okay. Now I want you to notice as the cylinder fills, the height is changing, but is the radius actually changing of that water in there? And hopefully the answer you see is no, right? Because as we fill up, like sure, it's getting taller and taller, but this radius is actually just staying the same. That radius is not changing. So let me put this down so I don't spill it. So what we have here is a radius that is constant. So let's go ahead and start with this equation. So my starting point is v equals pi r squared h. Oh, I should move that 2 back to its proper spot. So now when I want to solve this problem, because my r is constant, I can plug it in before taking a derivative. So because that radius is not changing, that radius is always 5, no matter how full with water the cylinder is, I can just plug that r equals 5 right in there. Okay, so that's saying my volume is just pi times 25h. And I can do that before I take a derivative because it's constant. So now I take a derivative, I get dv dt is 25 pi times dh dt. They told me the dv dt is 3. That was given in the problem. That's a bad 5. So that tells me that my dh dt is 3 over 25 pi. H is a height, that's in terms of units, that's inches. T is a time, that's in terms of minutes. So the units are inches per minute. So again, really one of the keys here, when is the only time you can plug in before taking a derivative? It must be constant. Okay. If something is constant, you can plug it in before you take a derivative. Any other time, if that constant is changing, in the cylinder, the radius and the height are both changing. We can't plug this in until after we take a derivative. But if it's constant, you can plug it in as soon as you like because it's not a changing quantity. Now, what if both the radius and the height were changing? So what if I had some weird cylinder that was expanding outwards while it was expanding up? Well, in that case, what I would have to do, I'd have a volume equals pi r squared h. I would have to use the product rule. And we're going to see some stuff with this tomorrow. But if I had to use the product rule in this, I'd just say, okay, dv dt is, okay, pull the pi in front. So it's r squared times the derivative of h plus h times derivative of r squared, which is 2r dr dt. Okay. And then I have more things that I need to plug in and be aware of when I went and solved that problem. Okay, but in this case, we were good because that radius wasn't changing. Okay, and then you might get some other shapes besides spheres, cylinders, cones, that kind of thing. If you do, just give you the equation, right? If they tell you, volume is like 30x squared over 3 plus x, well, that's fine. Like, just go ahead and use the quotient rule, and to take your derivatives, use your dx dt and so forth on each term. Okay, well, guys, I hope this helps. There's some good shapes. I think the more you do these problems, the better you're going to get at them. And I'll be back in the next video with some more. I'll see you guys soon. Bring me questions in class.